You're watching Stand Up and Scream. I'm your host, Desiree Rose. Today, our guest is Bob Essertier. He is a physicist, an inventor, a mountaineer, a daredevil, a former mayor of Hermosa Beach, and founder of Vertical Power Systems, a company that is making innovative wind turbine products. Thank you for coming on our show.
Oh, you're welcome.
It's a pleasure. Tell us about yourself.
Okay. As far as the wind turbines go, I went about 5 years ago to Holland to buy a vertical axis turbine company. And
what is that?
Okay, vertical axis. The wind turbine, most people think of something that spins like this, a big propeller, 3 blades that spin around like a big propeller. A vertical axis spins this way. It looks something like an egg beater. So it spins around. You have 3 blades. The advantage of the vertical axis is that the air is striking the blades all at the same speed. On the propellers, you have the hub where the air is going relatively slow because it's closer to the hub, and so it's not spinning fast enough. At the outer edges, we're spinning at 200 miles an hour, and so you end up with a net drag on the outside and nothing in the middle. So you only have the real work being done in the inner third, or the middle third. On a vertical axis, it's all spinning the same speed, and so you can have 100% of the blade surface doing work. So I went to Holland to buy this company called Turbine, and they had a helical-shaped blade. Asked them a bunch of questions about how it worked, and basically they couldn't answer my questions. They really didn't understand it. It was just, this works, and so we're going to make these and sell these. I was uncomfortable with that, and I didn't understand how they worked either. It seemed very unintuitive. Part of the things that bothered me is why, when it gets really windy, does the power fall off to nothing? That it could only work in a certain speed range.
The vertical systems?
Power, yeah, it could only work in a certain speed range. And also it took a very powerful motor to get it up to speed. They're not self-starting. You need a motor to bring it up to speed.
So they're not propelled by the wind and only the wind?
You need a motor to get them up to speed. You get them up to a certain critical speed, and then they would work. And then they can't go any faster. And
what about the other kind? Are they propelled by a motor as well?
No. No, those can be self-starting. So I was intrigued by this, and I went back to my home in an island in southern Brazil, and I thought about it, and I thought about it, and I thought about it. I was just intrigued by this problem. And after a couple months, I figured out how it worked, how all the science works. I applied the standard fluid dynamics theory and realized how these things work. So I had an intuitive feeling for how a vertical axis turbine worked. And I also figured out why they have these problems. And how—
Can you share that?
Yeah, the problems being self-starting and the power falling off. And then what I discovered was that the blade was stalled for most of the revolution. That you either had to spin very fast, like 5 or 6 times the speed of the wind, or it's going to be stalled for most of the way around the revolution. What happens is you'd have like a sweet spot, and the sweet spot would was amazing amount of power, but then it would sort of coast and actually being braked in
when it was fighting it, right?
Yeah, when it's fighting, especially when you're going upwind, it would be fighting. But most of the time, it's being stalled. The blade's stalled. The air is hitting the blade at too great an angle, and so you end up with a lot of turbulence on the blade, and it's not doing any good.
One question.
Yes.
When one blade is stalled, isn't another one rocking?
Yeah.
Okay,
yeah.
So then doesn't it kind of make up for it?
It makes up for it. Yeah,
right.
It makes up for it, and so it works. And so it works. So I asked myself the question: what if you're able to get the blades optimally positioned throughout the whole revolution? What if you were able to stop for a moment and turn the blade so it hit the air perfectly, so the blade wasn't stalled? And what I discovered is the power absolutely explodes. You are driving this for almost, there's only like 5 degrees when you're going perfectly upwind or perfectly downwind. There's only about 5 degrees on either side when it's not being driven. And when you're going straight across, sideways to the wind. When the blade is positioned perfectly, when it's optimally positioned, the power is enormous. It just explodes, just goes through the roof. So the question was, what would happen if you were to be able to position the blades? And the answer is, it's an amazing amount of power. Now, nobody would dispute that. This is not, this isn't rocket science. This is basic fluid dynamics and very solid science. This isn't anything weird. So I asked the question, why haven't people done this? And the answer is because it's really hard. How do you do that? How do you position it when this thing is changing? All the conditions are changing constantly. So I thought about it, how you could do it, and the answer is you get two parts. First part is to figure out what the air is doing exactly. Second part is then to use motors or something to get the blade into the right position. Now, the first part, there was nothing that existed that can read the wind. We're talking about milliseconds, even microseconds, about reading the wind, because the wind is constantly changing. You've got all these different conditions. You've got startup conditions, you've got transition conditions, you've got very high winds, you've got turbulence, you've got all these conditions. You have different wind conditions on one side of the turbine than you do on the other. And to get this optimal performance, this fantastic explosion of power, you have to have it positioned perfectly within about a degree of what's ideal. If you're off 2 degrees, you lose about 5 or 10%. If you're off 3 degrees, you lose 40%. If you're off 5 degrees, you've lost everything. So you've got to hit it dead on. You've got to be really accurate.
And you say the wind is always changing.
And it's always changing. Any child knows that. When you stand out in the wind and you look at the trees, they're bouncing around and the wind is blowing. It's coming from here, it's coming from there. It's constantly changing. It's not a wind tunnel. A wind is very fickle. It changes, it gusts, it stops for an instant, it comes back full force. And so you need to make these changes very quickly. And I realized that I could do it if I used some real high-tech stuff. For one thing, I measure the wind, what the air is doing, with these little high-tech pressure sensors, which I embed in the blades. The pressure sensors, I'm pulling 10,000 times a second. So I got 3 blades, and I've got sensors in the blades, pulling these 10,000 times. It comes into my computer. The computer figures out what all this means and figures out precisely, really, what every molecule is doing in the vicinity of the turbine in microseconds.
Is that an expensive addition to your normal wind turbine?
No, it's amazing. These little sensors I have, they're actually manufactured for cars, and so they're made by the millions, and so I'm getting them at very low cost.
So it doesn't up the price
tremendously,
tremendously, huh?
But these didn't exist 10 years ago. They didn't have anything like this.